Are you all able to hear me? If you are able to hear me, kindly write in the chat box that you are able to hear me.
Yes, ma'am.
Okay. Then I'll start my class. Anyone else said to come? Anyone else said to come? Or shall I start?
Yes, ma'am.
Okay. Okay. So today we'll be seeing, in last class we have seen indexing, right? Last class we have seen indexing. Okay, we have seen the different types of indexing. Like there are three types: primary indexing, cluster indexing, and secondary indexing. Okay, those are three types. Today we'll see what are the different actually indexings. Okay, we have seen yesterday those were single level indexing, but today we'll see the ones which are multi-level indexing. Okay, now single level indexing was that you had an index table, okay, which is having what do you say, key and pointers. Basically for indexing you had index table which is having key and pointers, and that pointers are pointing to your hard disk. Whereas in multi-level indexing what happens is you have an index table which is pointing to one more table, one more index table, and that index table is then pointing to your hard disk. Now why it is needed is because of the data available. Now suppose you have 50,000 to 10,000 50,000 to 80,000 records in your hard disk, okay, and you need to access them. Okay, now how do you access with help of indexing? Indexing is basically nothing but storing some data or storing some key which is pointing to that data. Now if you have 50,000, okay, now suppose from that 50,000 if I take 5,000 records in my index table. Now accessing that index table also is a difficult issue, or it's an issue basically. So what they do is indirectly we have an index table which is again pointing to some index table. Okay, they can be more than one index tables. Okay, one first index table is pointing to one more index table. That index table is again pointing to a hard disk. Okay, so it will be more of like this. Let me show you. Okay. It will be more of like this. Okay, where you have an index table at top which is pointing to some other index table. Now this is pointing to some other index table, and at last, no, sorry, these are two index tables. This is first index table and this is the second index tables, and these are all where your data is stored, nothing but your hard disk. Okay, now that is nothing but called as multi-level indexing. Now next will come for something called as ISAM. This is a part of index. This is the part. This is one of the type of multi-level indexing. Okay, it is called as indexed sequential access method. Okay, and in this, what happens? You have a key, you have a pointer. Okay, you have a key, you have a pointer. But here, if you have n keys, then you will be having n plus 1 pointer every time. Okay, if you have n keys, you will be having n plus 1 pointers. Okay, now what happens here is, suppose you have a root, you have again intermediate parent. Okay, and you have some entries available here all. Okay, now suppose you have an entry, let me take like this. Now suppose you have a root. Okay, you have a root which can hold only 2 keys. Now if it is 2 keys, 2 plus 1 3, you have 3 pointers here. Okay, you have 2 keys, then 2 plus 1 is 3, you have 3 pointers. Okay, I hope you can understand this. Okay, and this is the root, this is intermediate level, and these are all the leaves, which is nothing but where you can access your data. Okay, and this should be in same level. Okay, but for ISM it's not required to be in same level. Okay, now how does it happen? Suppose you want to insert, you have this data, now you want to insert 23. Okay, so we'll go to root, we'll search here. Okay, since 23 is less than 40, we'll move towards left. Okay, again we check it, 23 is greater than 20. Okay, so we go to the right side of it and try to insert here, but you can find that 20 and 27 is already inserted. Then what we do in ISM is we extend it, that is nothing but we give one more pointer and create a one more page there. Okay, we add one more pointer and create one more page, that is nothing but overflow page, basic overflow page. Okay, and like that you insert 23 here. Now same thing, let us go for 48. Now 48 means it is greater than 40, so go to the right node. Okay, and here 48 is less than 51, so go to the left. Here you have 40 and 46 already. Okay, so here you have already, it is filled. So what we do is we create an overflow page, we assign a pointer to it and insert 48. Okay, then again 41 also same thing, and with the 42 also same thing. Okay, and your limit is of a particular index file or index page, anything, limit for key is only 2. Okay, just a minute. I hope now you are able to hear. I hope now you are able to hear me. Is it audible? Okay.
Yes, ma'am. Yes.
Okay. So here basically whenever you are trying to insert and that particular page, whenever you are trying to insert and that particular page is filled, so what do is we create a one more page and a pointer which is attached to it. Okay, that's the simple concept in ISM. Okay, whenever you are inserting and that particular page is filled, you create one more page, that is nothing but an overflow page, and attach a pointer to it. Okay, so that's what 23, 48, 41, 42. I hope you have understood this. Next, the most important concept is B plus tree. Okay, and let me say you all, in 5th unit you'll be having single level indexing, multi-level indexing, and hashing. These are the 3 important concepts which will come in your exam. Okay, so you need to concentrate on this. Next is B plus tree. Now B plus tree is nothing but, I hope trees concept has already been covered in your data structures. Okay, so I'm not going in detail in that, I'm just speaking about B plus trees. Okay, now your B plus tree is basically a balanced tree. Okay, but what is the basic extra in this is, here you will be having the leaf nodes. I've said you all what is leaf nodes. Leaf nodes is nothing but where the data is available basically. Okay, So these leaf nodes are interconnected to each other. It's nothing but double linked list. It's nothing but type of double linked list here. Okay, you can go front and back. Okay, through the root, you can find the leaf node, you can go front and back to search the data. Okay, that is the main one advantage of it. And here non-leaf node or nothing but, let me say, the root is basically, you will be having keys. If the keys are m, or let me take 4 keys are there available, okay, in your root node, then the pointers will be 4 plus 1, that is 5. Okay, and all the data will be stored in leaf, and leaf should be in same level. As we have seen in ISAM, these are not in same levels. You have here and you have overflow page, but in B+tree all should be in same level. Okay, that's what you say it as balanced tree. Okay, next we'll see an example for this. Here you are having a root, okay, and for this root you have leaf nodes, and each leaf node is connected to each other with double linked list. Okay, now suppose I want to search value 5. Now suppose I want to search value 5. Searching is similar to ISAM here also. Since 5 is less than 30, I'll go to the left pointer and I will start checking here. Okay, now I found my 5. Okay, after going to left. Same with 15. 15 is greater than 13. Okay, it's greater here, but here there is no value of 15. That means that particular data is not available. Okay, now next, after searching, you have insertion basically. Okay, now suppose we'll see this scenario and I'll say you what to do. Okay, now say this here. Suppose I want to insert 8. I want to insert 8. So where will I insert 8? 8 is less than 13. So I'll come to left. 2, 3, 4, 5, 7. After 7, I'll try to insert 8 here. Okay, now this is now this got imbalanced. Okay, now this got imbalanced. Basically that means here you have only 4 spaces available which is filled. Now if you add 8, what happens is you have to split up this particular leaf, okay, to adjust it back, because we are saying B+tree is basically a balanced tree. Okay, so what they'll do is this 2 and 3 will split to left child, 7 and 8 here will split to right child, whereas 5 will go to root. Okay, I hope you are understanding. If I add 8 here, because 8 is less than 13, I'll come here and add 8 here. But this particular leaf page is already filled here. Okay, so what I do, I split this one. 2 and 3 will become left child, 7 and 8 which I have to insert will become right child, and 5 will go to root. That is one splitting. Now 5 has come here. Now even this got imbalanced because it is already filled. You can't insert 5 here. So what will I do? I will split it first. Okay, what will I do? I'll split. 5 and 13 will become left child. 17 will become my root. 24 and 30 will become my right child. Okay, now that is what they're doing here. So see here. Okay, what happens? 2 and 3 will become my left child. Okay, and this 5 I'm pushing there. And okay, and one more concept, whatever I'm pushing from the leaf page to the intermediate page, okay, that data should be stored in the leaf page. Okay, that data should be stored in the leaf page. And one more thing is that you can store it in either left child or in right child. Okay, you can store 5 either here or here, but basically usually everyone stores in the right child. Okay, now once I've stored this, 5 has gone up in the previous example what I've shown. Okay, 5 has gone up. Now because of this, the root node became unstable. So what I've done, 5 and 13 have become left child, and 24 and 30 has become right child, whereas 17 has become a parent child. Okay, here I want to say one more condition. If you have 4 keys, let it be leaf child or intermediate leaves. or intermediate one, which are intermediate indexes, sorry, intermediate indexes. If you have 4 keys, then minimum you should have 2 keys, okay, to make it a balanced tree. Okay, only for intermediate pages and leaves, but not for root. A root can have a single key also. Okay. Okay. Now after inserting, basically your, why is it not moving? So after inserting, it becomes like this. I had inserted 8. So my 2 and 3 became left child, whereas 5, 7, 8 became right child. Okay. And this 5 became my parent. Okay. And I have added, since 5 was a leaf, I have stored the data item in leaf again. Okay. Now you have 17 has root, 15, 13 is the right child for it. Okay, and 24, 30 became the right child. Okay, now next, if I, after inserting 8, now suppose I want to delete. Okay, I hope you all have understood insert. That is an important concept. If not, what I'll do is I'll forward my notes to you all. Okay, in detail how I'm doing it. I'll forward it to you all, or I'll share a link also if you all want. Okay, now next is deleting. I want to delete 19. Okay, I want to delete 19 and 20. Okay, from this one I want to delete 19 and 20. If I delete 19, we can delete it easily. Okay, 19 is greater than 17, it will come to right child. Okay, 19 is less than 24, it will come and search 19, it will delete it. Now once I've deleted 19, I have only 2 leaf data items available in that particular leaf. And what was my condition? It should have minimum half. If you have, suppose if you have in a particular leaf page, you have 4 keys, 4 keys is max, then half of it is minimum. That is the condition, and that minimum should be maintained. Now if I delete 19, you have 20 and 22. So there are 2 elements available, so it's okay. No need of distributing the pages again. Now suppose if you want to delete 20, now if I want to delete 20, okay, here, now what happens if 19 is already deleted, so there are only 2 elements. Now if I delete 20 also, then it will become only 22. Now 22 is only 1 element, so the condition is not satisfied. So your condition does not satisfy. So what will I do is, I will make this 24 to become as left child, and this 27 will be pushed up. Okay, I'll make this 24 become the left child, whereas 27 I'll push up, and a copy of it will be in the leaf page. Okay, because data item are available in leaf page itself. Okay, so we'll see this. Okay, see here what I've done. When I've deleted 20, only 24 was left. Previously it was 24. I've pushed the 24 in left. Okay, and from here 27 I've pushed up, but a copy of it I'm keeping in leaf page because data item will be found in leaf page only. Okay, and this copying is done only for leaf pages, not for others, because you can find here 17. There's nowhere 17 here. Okay, now after this, if you want to delete 24, okay, after this, if I want to delete 24, now what happens? Again the same thing. What I'll do, I'll push this 27 down. Okay, I'll push this 27 down and make the, I'll push this 27 down, and now listen carefully. If I push this 27 down, if I push this 27 down towards left, okay, then this 29, what I'm doing is, if I'm trying to keep 29 up and 1 copy of it here, still this is getting imbalanced. This particular leaf is getting imbalanced. Why? Because I'm pushing 27 down. right? I'm pushing 27 down, and 29 I'm pushing up, and a copy of it is kept in leaf node. Okay, so now since copy of it is kept as leaf node, here only one element is available, so this is also a problem. So this 29 also I push it towards the left, so you'll be having next 22, 27 and 29, and 30 will be only element available here. Okay, I'll show you this. See here, once I'm deleting 24, here 24 was there at 27th page and up also. Okay, now once I delete 24, 27 from up come down. Okay, and you were left with only 29. Okay, 29. Okay, so we, and that what it made imbalance of that particular node. So we have pushed the 29 also to left, and 30 became the only parent here. Okay, now what was the condition I have said? Except the root. Except the root. For all others, the condition is the minimum number of keys present in that particular page. The minimum number of keys present in that particular page should be at least half. Okay, should be at least half. Okay, but here it is less than half. Now this also got imbalanced. Now what will I do is I'll push this 30 up. Okay, I'll push this 30 up. See, let us see here. Okay, 22, 27 and 29 has come here, so 30 is alone here, so I'll push this up, and this 5 and 13 also will be pushed up to balance it. Okay, balance the tree. That's what here. Okay, 5 and 13 is pushed up. Before 17 only was the root. 5, 13 and 30 is pushed up. Okay, and your leaves are adjusted based on that. Okay, I hope you all have understood this. If anyone who has not understood, if anyone who has not understood, still, if you have not understood, still, anyone who has not understood, or you all want me to give you all notes on this, because I have a notes of how you're doing it. Okay, if you have understood, shall we go for the next topic? Okay, so we have done with multi-level trees. So basically tree-based indexing is done. Next is hash-based indexing. Now, as if I know you all have also done with hashing. Okay, hashing is nothing but finding the key. Some key will be given, you should perform hashing on it basically. Okay, hashing is nothing but performing hashing, that is nothing but some applying some mod on some particular key. Okay, and what the output comes at that position, you enter the data, or at that position you save the data. Okay, basically. Okay, so today we'll see something called as extendable hashing. Okay, today we'll see extendable hashing. Okay, now what available in extendable hashing is, you have directories and you have buckets. Now buckets are used to store the data. Okay, whereas directories are used to store the address for this buckets. Okay, now how that is done? Okay, how that is done, that we'll see. I'll directly go to the data where it is. Yeah. Okay, so this is the basic where you have directories, that is 0 and 1. Okay, and you have empty buckets because we have not inserted anything, and index table or nothing but what you say here it as directories. You have global level 1 and global depth 1 and local depth 1. Now what it is we'll see later. First we'll see how are we inserting basically. Okay, now suppose if I want to insert, and what the 0 and 1s is there, that also I will see. Okay, suppose now we are inserting 16. Okay, so what is the binary format of 16? It is 1 0 0 0 0. So what we'll do here is, since we have global depth has 1, the last bit, okay, we are checking only the last bit. Whenever global depth is 1, we check only the last bit. Now what is last bit here? 0. Since it is 0, at the 0th position, it's there is a pointer which is pointing to one bucket. There we'll save the data as 16. Okay, so this is the output which you can see. Okay, so last bit is 0, hence 16 is stored at 0th position. Okay, it's not position, it's a directory. Okay, next, if I want to insert 4, so what is the binary conversion of 4? It is 100. So we are checking the LSB bit. Okay, that is 0. So at 0th position we have 4. Okay, same thing with 6. At 6 also the LSB bit is 0 if you convert in binary. So we are storing 6 here. Okay, okay, now next, is next is, if I want to insert 22. Okay, but the limit of my bucket is it can take only 3 elements in it. Okay, my limit of my bucket is it can take only 3 elements. Now I want to insert 22. Okay, and the last bit of 22, the last bit of 22 also is 0. Okay, the last bit of 22 also is 0. Then what happens? 22, it is also 0. But what is the limit of my bucket? It can take only 3 elements in it. The limitation of my bucket is it can take only 3 elements. So what will I do is, I will split the bucket. Okay, I'll split the bucket. Okay, so there'll be a mirror image of this bucket again. Okay, there'll be a mirror image of this bucket again. That is nothing but I will double the directories here. Okay, I'll do mirror image of this bucket and I'll double the directories. That is nothing but what I'm doing. Since I have 22 here, I'm checking the last bit. Last bit is 0. Okay, now if I do mirror imaging, then how will I identify if I have to insert in this bucket or the mirror image bucket? Okay, that for that difference, for finding that difference, we are now taking last 2 LSB bits. You can check here. Okay, what we have done is we have created a mirror image of this. Okay, yeah, we have created a mirror image of this first one and doubled my directories. Now what will I do is I'll start checking the last 2 bits, that is last 2 LSB bits. Now for last 2 LSB bits of 22 is 10. That is nothing but at 10 position you are inserting the data. Okay, now for this we shall again check if 16, 4 and 6 in which bucket they will go. Okay, because now we are checking the last 2 bits. That's what they have kept here. The global depth has become 2 and the local depth also we are making it 2. Why? Because we are checking last 2 bits. Okay, now we are 16, last 2 bits is 0 0. So at 0 0 position we are inserting 16. For 4 also last 2 bits is 0. So at 0 0 position we are inserting 4. But for 6 last 2 bits is 1 0. Okay, so at this position we are inserting. Now this one is nothing but mirror image of the first one, right? Now next, same thing with 24. 24 is 0 0. So in first position where the 0 0 directory is pointing out, at that particular bucket I'm inserting. Then again 10 also last bit is 1 0. I'm inserting in the bucket in which 1 0 is pointing. Okay, now same thing like this for other examples also the same way, only we should know how to split it. I hope you all have understood how to split it. Okay, or still anyone? I hope you all have understood this. Now, I'll give you all an example. Okay, for today, this much is enough. I'll give you all an example question. Okay, in WhatsApp group. I'll give you an example question for the WhatsApp group. Okay, thank you for today because time is up. For today, this much is enough. I'll give you the example and the data. PPT is also I will forward you all. Okay, thank you.